Okay, welcome Roxy and Jack and Marina and Sophia, Marquette and Jacqueline. Thanks for coming. We are going to jump to the quiz. Okay, so here's the quiz. And it says a study was done to look at the relationship between the number of hours, A, people exercise per week when they're in their 20s, and the age, B, at which they die. The results of the study are shown below. Okay, so we want to see, take a look. Is there a relationship between how much you exercise when you're young and how long you're going to live? And, the thought is maybe if you exercise more, maybe you'll live longer, but we'll see. Okay, write down the null and alternative hypotheses. Okay, so there's really only one answer to this particular one. So what is the null hypothesis? What is the null hypothesis?
Rho is equal to 0.
Yeah, so it's rho. I'll just write RHO because it's easier to type, is equal to 0. Okay, and that's always the case when it's regression analysis, and this is definitely regression analysis because we're looking at a relationship between two quantitative variables that are connected. We want to see if one goes up, does the other go up or down, or what happens. Okay, and then H1. Yeah, of course, if you inserted the rho into the equation, that's fine too. But I'm gonna let you don't have to. It's not a requirement. So sometimes I'll type it in instead of doing kind of making it look fancy on this so that you can see that you're allowed to do that. Okay. But somehow you have to note that it's rho. You can write RHO or you can insert the rho into the equation, whatever you want. Okay, what is H1?
That rho is not equal to 0.
Yeah, rho, whoops. Have the cursor in the wrong spot, there we go. Rho is, all right, not equal to 0. Any questions on part A? So for part A, whenever you're doing a regression analysis for a quiz or exam, it's always going to be rho equals 0 and rho not equal to 0 for the null and alternative hypotheses. Okay, then write down the test statistic and the p-value. So we need to go to the calculator for that. And I'm going to copy the A row. So what calculator number? This should be obvious, I hope. Which calculator do we use? Yeah, this is 24, regression analysis. This is the chapter we're in. And again, this is testing to see if there's a correlation between two things. That's always regression analysis. And the easiest way is to pop in the X ones. And I did copy and paste, so you got to be careful. 4092. So I got to put commas in there. 4092, 14, 7, 4, 12, and 6. And then the Y variables. So I can copy and paste. Missed. There we go. And now I got to put commas. 77, comma, 53, comma, 10. Now, comma 104, comma 61, comma 98, comma 86, comma 69, comma 91, comma 71. Any questions on getting this into the calculator? Okay, so now we need to go ahead and I might have popped it in the wrong place, but that's okay. I can get it. X, Y, regression equation. And we got to hit plot points. So there's our test statistic, 5.13 about. So let's write that out. That's t equals 5.13. And the p-value is equal to 0.00135. Throw some decimals in there. Any questions at all on using the calculator? All right, now it's time to state our conclusion. What do you notice about that p-value? What's important about it?
It's smaller than any level of significance we care about.
Right, it's smaller than any level of significance you care about. So by the way, if I don't give you a level of significance, I'll make sure that the p-value is either really tiny or really big. So it's going to be one or the other. If you could put commas between every number, then that's not going to go well for you because it doesn't read your mind and know that that 12, the 1,2 was supposed to be a 12. So yeah, be real careful about that. So that'll happen. So again, be careful. The good news is this is just a quiz. So this is the time to learn so that when you take the final exam, that's where big points are, a big part of the course. So don't make the mistake on the final. That's the most important thing. Okay, so we want to state the conclusion, and we know that the p-value is really small, smaller than any level of significance we'd ever use. So that means there is statistically significant evidence to conclude that there is a correlation between hours of exercise in people's 20s when people are in their 20s and how long they live. Any questions at all on part C? Any questions? Okay, then we go to part D. Part D is write down the equation of the regression line. So that literally is right here. I'm going to copy and paste it. That's the easiest way to write down. And technically, though, it's y hat. I'll just put a little hat there. Easier. Okay. And even if you use the equation editor, the hat it can be done, but it's really hard to put in the equation editor. You have to understand LaTeX, and I'm not going there. Any questions on part D? All right. Now interpret the slope of the regression line in the context of the study. So first, what is the slope? Maybe to 1 decimal place is enough. So what is the slope? Yes, 3.3. So the first thing is the slope is equal to 3.3. Okay, now that's not an interpretation. That's just writing it down. Now we need to interpret. And when I say context of the study, and this is very important because I see that in some of the exams, you don't listen to it. So context of the study means you better be talking about, you better write about exercise and longevity. Okay, if you don't write about exercise and how long someone lives, then you have not put it in the context of the question. Do not just write down the definition. Make sure you write it down in the context of the question. So how do we interpret this 3.3? Do you remember how that works? And again, the X coordinate are exercise hours, and the Y coordinate is how long the person lives.
As the number of times per week a person exercises in their 20s increases by 1, the age they die tends to increase by 3.3.
Okay. Yeah, let me fix one word. You said times, but it's hours. That just comes from the question.
Oh.
Right. Because it's an hours per week. But other than that, sounded good. So let's write it out. So or let's write for those who exercise an additional 1 hour per week, on average, they tend to live 3.3 years longer. I should give you a big disclaimer, by the way. I did make up these numbers, but I always try to make them reasonable. And if you do your research, you will find out that exercising is a good thing. Okay. You know, I didn't really perform a study and watch people until they died, but these studies have been done. So I always like to do a disclaimer when I'm, citing some numbers like this, but this is not from a research project. These are made up numbers, so they were pretty easy to use on the test, and that's the important. I mean, on the quiz, and it's important that I don't give you something that's too hard to use on the quiz. Okay, any questions on part E? Okay, notice, by the way, let me boldface the word tend and average. There's some very important words in there, is that you do not say that if someone exercises an additional hour per week, they're going to live 3.3 years longer. That would be wrong, because you don't know for a fact what's going to happen to any individual person. You can only talk about an average tendency. All right, interpret the y-intercept of the regression line in the context of the study, or explain why it is not relevant. Okay, so for the y-intercept, what's the x value for the y-intercept?
0.
0. Okay, does that make any sense? Can x equal 0 for this particular study?
Yes.
Yeah, no, it can, but check it out. There's a data value of 0. If there's a data value of 0, it can equal 0. There's no question about it. Is that clear? Okay, then you always want to look at the different things to see if it makes sense. What is the y-intercept? What number is it?
57.5.
Yeah, 57.5. So let's write this down first. The y-intercept is 57.5. Can that happen? Is that a possibility?
Yes.
Yeah. Someone could die at 57.5 years old. Okay, that does happen. Okay, that's what we're talking about, is how long people live. And someone could live 57.5 years long. Okay, definitely happens. Okay, so there's no problem with that. And we saw that 0 is not a problem. We also saw that 0 is not far from the data values, because that's the other thing. In fact, it's one of the data values. So is the y-intercept relevant?
Yes.
Yeah, the y-intercept is definitely relevant in this example, because the 3 conditions are no issue, right? Again, 0 is a reasonable number. 57.5 is a reasonable number for lifespan or age of life. So, and 0 is not far from the data values, from the x values. So now we can use it to predict. Remember, if x is 0, y is 57.5. X is 0 means 0 hours of exercise, or in other words, our best prediction for someone who does not exercise at all? Okay. Any questions on how I turned 0 into does not exercise at all? Is for that person to live 57.5 years or die at the age 57.5. It's the same thing. Any questions at all on interpreting the y-intercept? Okay, and notice this is a prediction. It does not say we know it's going to happen to the person. It's just a prediction. Okay, next. Use the regression line to predict how long someone will live if they exercise 11 hours per week when they're in their 20s. What do we have to do? It's really easy if you know what to do.
Plug 11 in for x in the regression equation.
Yeah. So we plug 11 in for x in the regression equation. I think the easiest way of doing that is pop this guy in. I'm going to copy it. And then I'm going to scroll up, hit scientific calculator, go over here, and then change the x to a times 11. And notice it's 94. So if they exercise 11 hours a week, 94 years old. Okay, does that mean that if you make someone exercise 11 hours a week when they're in their 20s, they're going to live to 94?
Nope.
No, it doesn't mean that. Okay, again, causation is not part of regression analysis. You can't do that. Okay, these are predictions based on numbers. They're not matter of fact statements. Any questions at all on part G? Okay, then finally, part H. Okay, interpret R squared in the context of the study. So first thing, let's go back up to the calculator. R squared was, I like to use 2 decimal places, especially in this case, because it rounds so nicely, 0.79. So let's write that down. So R squared is 0.79. And now let's interpret it. So how do you interpret 0.79? Any thoughts? Okay, 79%. And what about it? Context of study, so you need to be talking about exercise and lifespan here. Maybe I should say lifespan and exercise. Okay, give you a moment because.
Well, don't you like first usually say that there's a lot of variation in the age of death? For people who exercise different amounts, or
yeah, or just for the general public.
Oh, okay. However, if you look at a specific class of people who exercise a particular number of hours, the variation in their age of death decreases by 79%. Or their variation in, for that particular class is reduced by 79%.
Yeah, so if you look at people who all exercise a known number of hours, the variation of age of death on average is reduced by 79%. Okay, so notice is exercise a good predictor based on this for age of death? What do you think?
Like relatively, yes.
Yeah, it's a very good predictor, right? 79% of the variation is due to how much people exercise. Okay. Whereas only 21% is due to other factors, which could be genetics or I don't know, how they eat or lifestyle or who knows. Okay. And again, I'm making up these numbers, so don't, quote me on this. But I bet within 20 minutes, if you looked out and, went to our library or a website and looked it up, I bet people have done this and they've researched this. And I don't know if R squared is 0.79, but I bet it's not that small because I know that I've definitely heard that exercise is good for you. And I'm sure you've all heard that too. So I try to make reasonable things when I'm putting in problems. Any questions at all about this quiz? Any questions about this quiz? This is the penultimate quiz. You know what that means?
Second to last.
Yep, penultimate. It's one of my favorite words. It's a cool word. It's the second to last quiz of the quarter. And the last quiz will be?
On Thursday.
Yeah, last quiz will be Thursday. So can you say the lifespan increases by 79%? That would not be right. So the lifespan does not increase by 79%. It's the variation in lifespan is decreased by 79%. It's not the same thing as a lifespan is increases by 79%. In fact, the lifespan is increased on average by 3.3 years for every hour of exercise. Okay, that's the tendency of lifespan increase. So the slope tells you how much increase you have or decrease. Okay, on average tendency. But the R squared tells you how much the variation is decreased. Does that make sense? Yeah. So again, I want to remind you again, this is the quiz was the time to get confused. And they've done studies on this, statistical research, and they found that if you get confused, but you figure it out and you get penalized points, which means that actually is a little bit painful, then you're much likely to remember it when it matters, like the final exam. Okay, so you should be happy that you got a bit confused, because as long as you understand it now, because that means there's a really good chance that you won't make the same mistake on the final, because it tends to be more memorable. Okay, people tend to remember the obstacles they've gone into and then hopefully not have the same issues that they had before or the same mistakes. Any questions at all on this regression analysis problem? Okay, I want to let you know, this is a promise. You are going to get a similar question on the final exam. It's not going to be the same. It's not going to be about exercise and lifespan. Okay, but you are going to be getting a regression analysis problem, and you need to be able to do all these different things. So definitely, take this one seriously, because this is on the final. Okay, but not, yeah.
So I looked at the module for the final exam, and it says it has 28 questions, but there's only 24 calculators. So would there be more for some?
Okay, I'm going to talk more about it on Thursday. So let me tell you why it looks like it has so many questions. It's because there's a bunch of true false questions and a bunch of matching questions that are quick.
Okay.
So the number of questions is not a good idea to even think about. Does that make sense?
Yeah.
Because some of the questions are really deep, like the one we just did here. This one takes 20 minutes, right? And then some are quick little true falses that take 10 seconds. Does that make total sense?
Got it.
And the true falses that take 20, a minute or whatever, those are worth 2 points or 3 points, something like that. And there's matching ones also. And then these long ones are worth 15 points. So the number of questions is not, I would just ignore that when you're worrying about their studying for the test. The number of questions is pretty meaningless. Okay, hopefully that makes sense. And the reason for that is that the true falses and the matchings, those are computer graded and it has its own way. So, had we not had COVID, we'd be in class right now and you'd be taking the final and it would be one question with like an A, B, C, D, E, F. Just let you know how I would normally do it. But Canvas has its way, and so I have to do them separately. So sorry about that if it's confusing, but it's a Canvas thing. Okay, any other questions about this quiz? Any other questions? Okay, again, so you want to make sure you get good at it so that when the final comes next week, you can do these kind of problems because you're going to have exactly one problem that has these kind of questions on it. All right, so let's go and get to the next piece, which is Q&A. Any questions at all about anything? Okay, and while you're thinking about questions, I always like to give you a reminder of what's coming up. So again, today is our last day of regular lecture with new statistics. Then Thursday, you'll be taking a quiz on what we're talking about today. And then after the quiz is review for the exam. Okay. And one of the things that I'm going to give you some extra homework that's due on Thursday, and that is take a look at the different topics and see which ones you feel like you need extra practice with me. And so that on Thursday, when I ask you, what do you think you need practice, you'll tell me, and then I'll give you some practice problems, okay, that we'll work on in class. So that's something to be thinking about between now and Thursday. It's not like long homework. It's just, coming up with things throughout from the beginning to the end of stuff that maybe was a little confusing for you or you forgot about. Now you need to practice it or whatever. Okay. So that's just a note. So that's on Thursday. And then a week from today is your final exam. And it's a 2-hour final because that's what the college says. And in fact, let's see. This one. I do have to get to it. Just a minute. So the final exam is a 2-hour final. And if you go to it, it's from 4 to 6. And what I do is I do whatever the college tells me I have to do. So that's the time that you take your final. Okay, so it's not your normal 3:30 to 5:50. It's from 4 to 6. Okay. And again, I just follow the schedule, and that's what the final schedule is. It actually says 4 to 5:50, so it's officially over at 5:50. But because we're doing this online, it takes some more time to type, and there might be issues. I'm giving you an extra buffer of 10 minutes. Okay, in case you need those extra 10 minutes. But it's officially 4 to 5:50. But if you have to go an extra 10 minutes, I'll let you do it. So that's the final exam. And you'll notice after the 22nd, there's nothing. Course is over. And we don't have lecture a week from Thursday. The class is completely over. Okay. So more than 20, again, don't worry about how many questions. So for example, this quiz, how many questions was this quiz?
7.
Okay, not according to Canvas, is one question, right? Question 1, and that's it. You go down, there's no more questions. This would be a 1-question test. So trying to look at how many questions you have is ridiculous, because this is a 7-question, whereas a little true false, it takes 5 seconds, is that's still counted as a 1-question problem. So a number of questions is not something you want to even think about. Okay, but it's not a short exam, but it's most of the questions, a lot more than half of the questions are really quickies, if that tells you anything. So don't get too frightened by seeing the number of questions. Okay. Questions? Any other questions? Okay, I have a question for you. It'll be a nice summary of what we've been doing the last month or so. And that is, what hypothesis tests have we already learned? What can we test for? On Thursday, you're going to break down which each question is again. Not quite the details that I did before, because I want you, because it's comprehensive, but I can't, as you mentioned, if I asked you a question about everything we've done, it would be too long. So I can't quite do the details, because I want you to basically show that you know everything we've learned. Does that make sense? So I'm going to give you some things, but not as much detail. Just let you know about that. Okay, so what kind of hypothesis testing have we already had? What can we test for? From the beginning of hypothesis testing, which was chapter 9. Okay, good. So independence, homogeneity, correlation. Okay, so we want to see is two variables independent. Okay, when they're qualitative, do they have the same distributions when they're qualitative? And then there was correlation, which we just did, which is when you have 2 quantitative questions, is there a correlation between the 2? Okay, we've done a whole bunch more. We've done, a test for proportion. Is a proportion less than a number, greater than a number, not equal to a number? What else have we done? Yeah, we've done the same thing with mean. Have we seen, is the population mean less than a number, greater than a number, not equal to a number? What else? You're doing great on listing them. Here's a hint. Mean with data. Okay, that's still a mean, but yeah. Here's a hint. Chapter 10. You haven't listed anything for chapter 10 yet. See if you remember chapter 10. Yeah, we're looking at, what about difference though? Be a little more specific. Okay, test for independence. Yep, that's definitely one. I think that was already up there. But yeah, we definitely need test for independence. And you say difference, but what about difference? Because there were actually 3 different tests for differences. In chapter 10. So what kind of differences? Or difference between what things? a good exercise to go through it all, since again, you got an exam in a week.
Wasn't it different than or greater than or less than?
Okay, so those are the types of tails you can have, which was true the mean of just a single proportion or mean. But what did we find the difference of? And the hint is you did it for your project. Yeah, 2 parameters. Good. So you found the difference between 2 means, and you found the difference between 2 proportions. I'm going to get a little more specific. You found the difference between 2 independent means, and you found the difference between 2 dependent means and proportions. And the last one that no one mentioned, it's interesting, is goodness of fit. Okay, does a population fit a known distribution? So goodness of fit test. All right, now comes a more interesting question. Okay, or a different question, but related. So we just wrote down or talked about all the different hypothesis tests we've already done. What haven't we done yet? What don't you know how to do a hypothesis test for? Okay, I'm not looking for a title of a test, but what don't we know how to do something? Probability. So what do you mean by that?
Like, I don't know if there was a hypothesis test for like how likely something is to.
That's kind of goodness of fit, right?
Oh, yeah.
Yeah, that's kind of goodness of fit. So if you have how likely the different outcomes are, is it what we thought it was or not? That's really goodness of fit. Okay. What haven't we done? There's actually a whole lot of things we haven't done. And there's one we're going to do. Okay, average number of variance. Okay, so a test for standard deviation or a test for the variance, either way, that we haven't done. And I'll mention something. And I'm sorry if you're sad about this, but I used to do this, but there was just too much in the class. So I got rid of that. And I got rid of it because I noticed a lot of other instructors throughout California got rid of it. And I try to be uniform. I try to do what everyone else is doing. So there is a test to see if the standard deviation equals a number or if 2 standard deviations are the same. And that we haven't done. And I'll let you know we're not doing that one. But there's definitely a statistical test for that. And you need to take a more advanced step. Yeah, so beware about the name ANOVA because that's not going to help at all. The name ANOVA is very misleading. That's why I'm just asking you without even saying ANOVA. All right, maybe you need a hint. So we found, for example, a test to see if a mean was a number. And then we compared 2 means to see if the 2 means were equal or not. Could we go beyond that? Can you think of what going beyond that would mean? What would be the next step?
Multiple means.
Multiple means, and in fact, more than 2, because 2 is multiple also, but more than 2 means. Okay, and we have not learned how to do a hypothesis test for more than 2 means. And by the way, there's a whole lot of other things we haven't learned yet. We haven't even touched medians. Remember that way back when? There's all kinds of hypothesis tests for medians, okay, or tests for quartiles or all kinds of things like that. And we don't do that in this class. That's advanced statistics, so we're not going there. Other things we haven't done is we haven't delved deeper into, for example, goodness of fit to find out what if it's not the same distribution, which part of it is different. Okay, and we don't do that. That is, there are tests for that, but we're not doing it in this class. On the other hand, we're going to be looking at a test to see if multiple means are all the same or they're not all the same. Any questions on that idea, that the fact that we haven't learned how to do that yet? Okay, so for example, do you think college GPAs are the same for every state in the United States? What do you think?
No.
Okay, how would you find out? How would you be able to show that they're not the same?
Do a hypothesis test for the average GPA.
And how many different GPAs would you have to look at?
Over 30 or over 30.
Okay, actually a whole lot more. Okay, if I did 31 GPAs, I haven't even covered all the states in America. How many states are there in America? Hopefully y'all know that one. That's not a math
Are
thing.
you actually asking that question?
Yeah, you bet. Well, not everyone knows.
That
Not everyone knows how many states are in America. I'm not kidding.
It'd be sad if they didn't.
It is sad, but that doesn't
honestly,
mean.
we should give Hawaii and Alaska back. We took those places
I
without.
don't know. Hawaii and Alaska are wonderful places to visit.
Yeah,
I wanna
but
get
we
out.
should not. They should not. We took them. We colonized them. That's not okay.
Well, we took the whole country.
That's true. That's true. We suck.
Yeah, you think we didn't take New York from
This
the
is
Native
terrible.
Americans? And yeah, no, we
No, yeah, totally.
did what we did. Okay. Yeah, we did what we did. The good news is that none of us did it. Okay. There's nobody alive that did that. That's the good news, is that the colonization happened not by us, but by, predecessors. But the point is that there are 50 states in the United States. So you would have to ask over 30 from every state. Okay. 30 people wouldn't, 31 people, period, or students is not enough, because you wouldn't even hit one in every state. So good luck comparing them all. So one thing to note is that you're often going to need big sample sizes to be able to do comparison like that. Okay. If you're only comparing maybe 3 things, that's not too bad. But if you're comparing 50 different states, it's a big project. Okay. And by the way, I couldn't ask you to do one with, where I asked you to do the calculator work on it. It's just way too much typing. Okay. And in fact, my calculator doesn't even have 50 places to put in. You have to use my spreadsheet program. Not does. So just note is that there's a lot of things where you're comparing many different things, like the states in America, and then there's 50 different states, or the counties in California. And don't tell me you're dumb, that someone would be dumb if they didn't know how many counties there were, because then I'm dumb, because I'm not sure how many counties there are, but I know we got a lot. I've lived in 6 of them, I think. And I'm not even close to all of them. So you could do the same thing with counties in California. Or there are many different studies you can do where you're comparing groups, but not just 2 groups, but many groups. And when you do that, we do what's called ANOVA. Any questions on the idea before I get into more details? Okay, so here's the bad news, and please don't shoot the messenger on this. The word ANOVA stands for analysis of variance. And I spelled it in a weird way with capitalization. And my guess is hopefully all of you can see why I did this weird capitalization thing. Because if you write down analysis of variance the way I've written it, and you only pick the capital letters, then you get ANOVA. Okay. And again, I'm not the one that did this. Some clever person decided to do this. And then
That's what happens when you let STEM people create acronyms.
Yeah, it wasn't me though. Wasn't me. Okay. But it does test to see. So what I created, by the way, is a calculator. So if you hate the calculator, it's my fault. Sorry about that. So we all have our things that we did, and that's my thing. Okay. So ANOVA tests to see if several means are all equal or not. So one of the awful things about the name ANOVA is it's very misleading. Do you agree? Analysis of variance is a test to see if means are equal or not. Okay, so I want to give you a warning. It's just what they call it. And what I will tell you is a reason why they call it it has to do with the deep mathematics that lies underneath all of this, which I am not getting into and I never do in this class and still won't. But I'll let you know that there's some variance analysis that happens when you're computing, the p-value. But you don't have to know that because that's all going to happen in your calculator. But you can trust me that it happens because I got to do all that kind of stuff. So the analysis of variance is a test to see if several means are all equal or not. Okay, so H naught. H naught is pretty easy to write. So you learn from chapter 10, if you're comparing two means that were independent, then H naught was mu1 equals mu2. Do you remember that? So now we're just going to extend that. If we were comparing three means, we'd have mu1 equals mu2 equals mu3, and that would be H naught. Okay. If we were comparing, say, the example where we're looking at mean GPAs of all the 50 different states to see if they're all the same, the last thing you want to do is write down, mu1 all the way up 50 times, mu2, mu3, et cetera, et cetera. So you usually use a ... notation. So mu1 equals mu2 equals ... That means keep going until you get to mu(n). And for the state example, that would be mu1 equals mu2 equals ... equals mu sub 50. Okay. Any questions on that? Any questions? Okay. On the other hand, let's say we wanted to find out if the GPAs are, the same or different for the Cal State systems, the UC system, and the California Community College system. So in other words, the three major systems in California. Well, then you don't need ... You would just do mu sub CCC equals mu sub CSU equals mu sub UC. And that would be your H naught. Any questions on that? Any questions? All right, so I want to remind you something with hypothesis testing, and that is H naught is the status quo. If there's nothing like peculiar about anything, then the mean should all be the same, right? If everyone's doing it the same way, then the mean should be the same, right? The colleges, right? Okay, so of the mean of the 50 states or whatever you're doing. H1 is saying that H naught is incorrect. So let me ask you something. Could I write H1 for the alternative hypothesis? And then I'm going to go mu sub 1, and then not equal to, is that one, mu sub 2, and then not equal to, and then ... and then not equal to again. And then it's mu sub n. Is that correct? Is that what it means to say that H naught is not true? What do you think? So H naught is that, all the means are equal to each other, and H1 is that they're all different from each other.
Not necessarily, because some of them could be the same, but like all of them.
Exactly. I'm really glad that you caught that. So the first thing is this is wrong. So I'm going to write wrong. Don't write this. Okay. It's wrong because it could be like for the GPA, maybe Nebraska and Kansas have the same GPAs, average GPAs, but maybe Alaska's different than Kansas. And maybe California and Alaska are the same. Okay. But if you have any differences, even though a bunch of them are the same, then that means H naught is incorrect. So you get to reject H naught. Any questions on that idea? All right, so since that's wrong, how do we write down what's right? One more time on why this is wrong. So let's suppose I'm doing the GPA example because it's a nice one you can all hopefully understand. Let's suppose that California and Alaska have a mean GPA, both of them, of say 3.1. And let's say Kansas and Nebraska both have a mean GPA of 3.2. And let's say the rest of the country, every other state, has a mean GPA of 3.0. Then are all the mean GPAs the same? Is mu1 equals mu2 ... equals mu(n)? No. Are they all different? No, because California and Alaska are the same. Does that make sense? So that's why this interpretation of H1 is incorrect. Okay. So what we need to do is we need to say, how do we write what it means to say H naught is false? Any questions on that idea? And I want to let you know, when I first taught this class, I actually did it with symbols. And what I learned is that no one understood it and no one could figure it out, and it didn't work. So a few years later, I realized I gave up. Sometimes you got to give up. I tried every way I could think of. So then I went to words. So kind of in words, how do you say that H naught is false? How do you write an H1? Any thoughts? Because symbols are really hard, but words aren't too bad. Any thought?
Means all equal.
What's that?
The population means aren't all equal.
Right, but what does that mean specifically? Okay, let me write down H1. So I'm going to get rid of the wrong and let's put in the right. So H1 is that at least 2 of the population means differ from each other. Because if there are 2 of them, then that are different from each other, then they're not all equal, even though all the rest of them might be the same. But if they're not all equal, that you can grab 2 of them that are not the same. Maybe 3 of them, but maybe only 2 of them. Does that make sense? So that's a big deal. That is the alternative hypothesis. Okay, and the only adjustment you'll make is you would say, for the example I'm kind of talking about, is at least 2 of the population mean GPAs in 2 different states differ from each other. Do you see that? So you just throw in the context by talking about mean GPAs in 2 different states differ from each other. Any questions so far? Okay, so that's H naught and that's H1. I want to talk about the requirements before we do examples. What we're going to do, my plan today, is I'm kind of giving you the idea of analysis of variance and giving you what you need to have in order to perform analysis of variance. And then in our last 50 minutes or so, then we'll do examples. That's the plan today. Hopefully that's okay. Okay, there is a variation among the means I'm reading. Oh, I'm gonna go for the 2 population means. Okay, so next comes the requirements. And I want to mention these are tough. Okay, not necessarily tough to understand. They're tough to apply in the real world. Okay, some are harder than others. So the first one, this one we've seen before. Okay, so if we remember chapter 10, if you did a test for 2 independent means, then one of the assumptions or necessities was the sampling distributions must be approximately normal. And one way of getting that is to make sure both of the means, both of the sample sizes were bigger than 30. And another was to just know they're normal, or, okay. So, but this is much harder often with ANOVA. So as I mentioned, if you're doing ANOVA, and let's say you're doing my example with the GPAs in all the different states, there's 50 states, you need at least 31 in your sample for each of the 50 states to be able to use the central limit theorem to show normality. Well, 31 times 50 is 1,550. So all of a sudden you got a really big sample size, for your total sample size. So just a big note is that total sample size gets big often when you're doing ANOVA. Okay, but you have to do what you have to do, because if you don't have a large enough sample size, then you have to assume that you have normality, and assumptions are bad. They're usually false. Okay, any questions on that number 1? So again, we've seen number 1 before, but now I just want to remark that with ANOVA, it's harder because you're going to often have many different populations to deal with, or samples to deal with. Okay, number 2 is all population standard deviations are equal. Okay, so I will let you know that that is not something we're going to learn how to understand in this class. Okay, I mean, you know what it means to say it, but to actually check that it's true, that the standard deviations are equal, that's brutal. Okay, and that you need advanced statistics. We can't do it. Okay, and one of the key mistakes, there's been research on research projects. They call it meta research. So they research projects, and they found that there's a lot of errors in statistics people cite, even among peer-reviewed journal articles. And the biggest error is that people are not checking requirements. Okay, and sometimes it's because it's too hard to do. Okay, so that's just a note, is that you're going to think by the end of today that you know how to do ANOVA, but you don't know how to do these requirement checks. Okay, especially number 2, because that involves some more hypothesis testing, which we're not doing in our class. Okay, so all population standard deviations are equal. Okay, number 3 was the same assumption we've made for every single hypothesis test and confidence interval that have happened in this class. And that is, we don't have a bias study. Okay, if you have a bias study, then don't trust it. Okay, it's just a bad idea. So kind of the official way of saying it is you have simple random sampling, but really if you have a representative samples, then that's good enough. So if you do kind of a really good stratified sampling where you're doing several strata to make sure that you don't have bias based on any of the things that are probably going to be biased, then that's good enough. But it's very difficult in the real world to not have bias. I mean, even your project had some difficulty because you had to do a stratified sample or cluster sampling. That was just one strata. Okay, so you learned how to get rid of a little bit of bias, but to really do it right is difficult. Any questions on 1, 2, or 3? Any questions? Okay, let's go to number 4. Number 4 is actually quite easy. And that is the samples are independent of each other. That's usually the case, not a problem, but you just have to be aware of it. Where you can go wrong is by doing dependent samples. So for example, if you wanted to find out whether the average number of days a week that people wear red clothes, blue clothes, green clothes, yellow clothes, white clothes, and black clothes, and you want to find out if the averages are all the same or not, sounds like ANOVA, doesn't it? Because you're going to ask someone, how many days a week do you wear red clothes? And then you can say, how many days a week do you wear black clothes? Then you can say, how many days a week do you wear blue clothes? Right, etc. What's wrong with it? What's wrong with that study to try and do ANOVA? If you ask, let's say you ask 31 people and you ask the kind of a list of those questions for each, it's all quantitative, and to find out if there's a difference in the means. Any thought what would be wrong with that particular example? So you can chime in. I'm hoping you get it. So if you ask 31 people how many days a week you wear, and then the first question was red, blue was next, black was the next, yellow was the next, and you just listed the colors, and they had to fill in the numbers on the number of days a week they wear each of those. Ask 31 people, you got 31 data sets, they're all over 30, sounds good. Maybe use simple random sample to find your 31 people even. Maybe you knew the standard deviations were equal, but it's still not right. And what's wrong? What's wrong with using ANOVA?
It's not independent sampling.
Yeah, that would be dependent, because one person, if someone tends to wear red a lot, they're probably going to wear blue less, because hey, they just wore red. That means that, that's their color that day. Do you see that? So that would not be independent samples. That would be a dependent samples, many dependent samples. Okay, do you think there is a hypothesis test for that? Any guess? I don't see y'all jumping in. Okay, the answer is yes. Okay, so the answer is yes, there's a hypothesis test, but we don't do it in this class. Okay, we're done at ANOVA, and so if we haven't had it yet and it's not ANOVA, then we won't do it. Okay, but there are tests for just about anything. Okay, in fact, I remember I did some consulting work on some river analysis for the Forest Service, and they had something, and there was no test I'd ever heard of. I've taken a lot of stats, but you know what? I did some research and I found a test for it, and that's kind of how it is. Mathematicians have figured out a test for just about anything you could possibly do. Okay, so there's a test for it, but not ANOVA if it's dependent. Any questions on that? Okay, and then the last requirement is the samples were consistently taken. Okay, that one is very doable as long as you do it right. Okay, so let me tell you I like this GPA example. Do you think you could do this GPA study by yourself? Survey at least 31 people in every state in America? Yeah, probably not. Okay, probably not. It would be really hard to do that, not just because it's a large sample size, but it's all over America, and especially if you needed to do some face-to-face kind of study, you'd have to travel to 50 states. Might be fun, but it would take you way too long. So instead, the way it's usually done is you hire maybe one person from each state. Let's say if this might be for your business or, then you're going to hire people from different states, maybe one from each state to do a sample of 31, somewhat random study. Okay, representative sample of 31 people or 50, or if you want to do a little better. And you're going to have them do it. And the issue is that the person that you hire in Maine might be answering it asking the question slightly differently than the person asking in Oregon, because they're all different people. Okay. And that's not okay. So what do you think you need to do? Let's say you were in charge of this study to make sure the samples are consistently taken if you're hiring 50 different people. And I actually know from experience from when I was 11 years old. Told you that was one of my first jobs. I did surveys. Nothing to do with being a math person. I was 11 years old. Okay, so what do you think? What do you think you would do if you were in charge of the study? You've hired these people. What would you do before they went and did the study? Any thoughts? Okay, you give them all the same question, and that's definitely a good thing. But there's a little more to it. It's a lot more subtle than that. A lot of people will, the person you ask will maybe not understand quite what the question's asking. They're going to ask a question about the question. Okay, that's called reality. Okay, that happens. And then the surveyor has to deal with it. Okay, so here's what you do. Okay, and it's not what I did when I was 11, but something similar, is you have a Zoom meeting. And you have all 50 of them get together on Zoom. Okay, in the old days, you'd fly them out to wherever you are, but now it's a lot cheaper to use Zoom. And you do what's called a briefing. And that means you talk about how the study is to be done, how they're to ask the questions, how they're to respond to one of the respondents. If the respondent has a question to the questioner, to make sure that everyone is doing it in the exact same way. Okay, and that's the way you handle that the samples are consistently taken. You make sure that the time frame is similar. So for example, you don't want the people in Kansas asking in the summertime and maybe the people in let's say Nebraska asking in the wintertime, because might get different answers, depending on what time of year you ask for GPAs. Okay, so you make sure that you have consistency, and you do that by having a meeting. Okay, and the cheapest way is Zoom, kind of the new way. The old days, you'd meet up in person. Okay, any questions on the requirements for ANOVA? And if any of these don't hold, then you can't do ANOVA. Okay, it means you need to fix it. Okay, or do a different test if there's a test that can handle it, like for non-independent. Okay, but if you have bias, you need to fix it. If the standard deviations are not all equal, you need to do a different kind of test, which that's beyond this class. So just let you know there are tests for a lot of these things. Okay, similarly, if the distributions are not approximately normal, there's another test you can use. Okay, but if you have all these, you can use ANOVA. Any questions at all on ANOVA idea before we take a break and then do an example? Any questions? Okay, if there's no questions, it's 5:05. Let's come back in about 5 minutes or so. And I'm going to stop the share. And I am going to let y'all take a 5-minute break and come back. Okay, welcome back. It's a little after 5:10, and hopefully you had a good little break. Okay, so what I thought I would do is I'm going to start with an example that is in a published paper. So instead of doing an ANOVA, let's read someone else who did an ANOVA and see how they wrote it. And I want to warn you, published papers are hard to read because they're high level. So it's not simple, but I think it's good experience to see some papers, and ANOVA's like all over the place. Didn't even take me 5 minutes to find a good ANOVA example because they're everywhere. So let me share my screen. Okay, so this example, in fact, let's make it a little bigger. That's probably good. So this example, it was an article predicting students' academic performance by their online learning patterns in a blended course. So I researched some online, just typed in online in our library. To what extent is a theory-driven approach and a data-driven approach consistent? And I'm not going to read the whole article because that would take all day long, but I will let you know over here at the bottom. It says a one-way ANOVA revealed that the online learning pattern, which had the most learning events and was characterized by high proportions of viewing course contents and of performing problem-solving exercises, had the highest academic performance. So in this case, again, it takes a while to read this and kind of see what they're talking about, but it looked like they had some kind of quantitative study of academic performance. It could have been GPA or maybe the grade on the test or something like that. And they looked at different types of styles, okay, different learning patterns or different teaching patterns. And they found out that it did make a difference. They were not all the same because ANOVA shows that they're not all equal. Some of the patterns are the same. Some of the patterns are different, or maybe they're all different, but they're not all the same. And then a cross-tabulation revealed significant association between the self-reported and observational online learning patterns, demonstrating consistency of the evidence by a theory-driven and a data-driven approach, and triangulating the results of the two approaches. Again, I don't expect you to understand all this. It's not like it's high-level science or something, but it's, this is written for people who are researchers. Some people who are experts in this particular subject already. Okay, but I want to emphasize that, hey, here's an article and they're all over the place where ANOVA was used to show something, okay, to show that not all the means are the same, that it does make a difference for this. Sometimes you'll say that in this case, learning events is a factor, type of learning events is a factor in academic performance. You'll often hear the word factor to talk about that. Any questions at all on just kind of reading an article? Okay. Again, this is not a research course, but you'll probably be taking a research course. So you probably wouldn't be taking this class because research, upper division classes at the university usually have to look at research. And definitely if you get a master's degree, there's no question you'll have to write your own, just let you know. Okay, let us now that I've given you kind of a example of a high level stuff, now let's do more of an elementary stats example. Okay. And by the way, if you ever see the word suppose in something I wrote, do you know what that means? So I want to write it. I want to give you a disclaimer. You know what it means if I say suppose? Yeah, not a real study. I made this up, but a study could be done. But I made it up and I always try and, make it somewhat realistic. Okay, suppose that a study was done to analyze the racial differences for the distance in miles that people live from the nearest public library. Okay, so, doesn't matter what race you are, is race a factor in how far you live from the nearest public library. The data from the study should be R, sorry, are shown below. So we looked at the races and we have our whites, blacks, Hispanics, and then other races. And notice that, for example, this 15 means that this first person who was white lives 15 miles from their nearest public library. Whereas, say, the third person who was Hispanic lives 5 miles from the nearest public library. Any questions at all on kind of this study, this fictitious study? Okay, so the first question is, what kind of test do you need to use to answer this? We want to find out if there's a difference in the mean distance from the nearest public library, if you're white, black, Hispanic, or other race. What test do you think we'll need to use? Not a trick question. It's supposed to be easy, given that we're today. So what test? What hypothesis test? Yeah, ANOVA. ANOVA. It's ANOVA because we're looking to see, we got 4 different quantitative variables, and we want to find out if their population means are the same or not. Okay, and that's ANOVA. So always the first thing you want to do is decide what test you need to use. For the final exam, you're going to have to know. And we've had a lot of tests. Don't just say, oh, we're in week 11, so it must be the ANOVA, because that's not going to help you next week. Next week, you're going to have a bunch of things to do, and they won't all be ANOVA, that's for sure. Okay, any questions on the fact that this is ANOVA? All right, so now the first question I have is, what assumptions must you make in order to perform an ANOVA test? All right, what's the first assumption we have to make?
All sampling distributions are approximately normal.
Yeah, now, do we need to assume it or do we already know it? And why?
Do you want the requirements? Is that what you're asking for, or are you just?
Yeah, but why is it that we need to make
That is a correct answer.
That's a correct answer. Now I'm doing a follow-up. So a follow-up is, why is it the correct answer?
Because it's one of the requirements.
There's something more than that. There's something deeper.
Okay, but all I really need to know is that it's one of the requirements.
Well, on the final, I could ask you why. So just let you know that.
Solid, my dude.
So why do you have to? Why is it in this case that you have to make that assumption? No? Look at the sample size, for example, for blacks. What's the sample size? Yeah, less than 31, in particular, it's 4. So first, since the sample sizes are 6, 4, 6, 4, which are all less than 31, we must assume that the population distributions, or the distributions of distance from the library for each race are all normal. Any questions on the first assumption? Okay, had we had a sample size that, let's say the sample size for the Hispanics was 35, but the others are as shown, then we would only need to assume normality for whites, blacks, and others. So I want to emphasize that that's a piece of looking at the assumption. So you should always look at the sample size, because with a big enough sample size, you don't have to make the assumption. Okay, what other assumptions? What's another assumption we have to make? Yeah, they have equal standard deviations because there's no reason to know that they have equal standard deviations. Nothing up here says that. So we met that. That's an assumption. And again, the reminder is that's one of those we can't verify with elementary stats. You need advanced stats. Okay, so we need to assume the 4 standard deviations. Let me write population. Standard deviations are all equal. What's another one? What's another assumption we have to make? Can you remember? Don't see you jumping in. You need to assume there's no bias in the sampling. Or in other words, the samples are representative of the population. If they use simple random sampling, that would do it, but there's other ways too. Okay, that's one of those where standard deviation, that one you had to do advanced stats. This one, you have to find out how the sample was taken, and then evaluate whether there was bias or not. So that one's, the bias thing is not a mathematical thing. It's just to make sure that you've done it correctly. Okay, then there's other assumptions. Okay, were these independent of each other? What do you think? You're all being quiet. I don't see y'all jumping in. Okay, the idea here is that they probably are independent. It's this study would be very hard to do with dependent data. Good luck, finding 4, a white, a black, Hispanic, and other that are all associated with each other, and then find another group and then another group. That probably didn't happen. So maybe we can just say we need to check to make sure. that the four groups were independent of each other. They probably are, but it doesn't say it, so we got to check. Okay, and then finally, what's the last one? Do you remember? Now, see, y'all jumping in. Maybe I'll say we need to check to make sure that, again, so the last one, if you remember, that the surveys were all conducted in the same way. Okay, so they didn't like ask the white people in a different way than they asked the black people. Probably didn't, but you should always check that. Any questions on part A? Okay, let's go to part B. Show the details of the ANOVA test. State your conclusions in the context of the study. All right, so let's go to H naught. That's how we start. Remember, it's a hypothesis test, so you always want to start with hypothesis. So what's H naught? So what is H naught for this one? Any thoughts? Yeah, all means are equal to each other, but I'm going to put those in symbols though. So mu sub, let's go W for, whoops, W for white equals mu sub B for black equals mu sub H for Hispanic equals mu sub O for other. And then we got to do H1. What's H1? Yeah, at least two are differ, but let's put in the context of the question. So at least two races have different population means distances from the nearest library. Any questions on this? Okay, what's the next step? You should be used to this by now. After you write down H naught and H1, what do we do next?
Calculator.
Yep, we go to our calculator. And I'm going to scroll up so I got all this stuff. Okay, so we go to the calculator. And you can probably guess which calculator. As I mentioned, this is our last day of new material.
$25.
Yep, 25. So ANOVA. So we're at the end. It's a good feeling to hit that last button, isn't it? Okay, so we're on 25, the very end of the course. And it says enter the data value separated by commas. So data 1 was 15,411. And then 932. Data 2 was 12,166. Data 3 was 917.5. And then 1471. And data 4, 1811.28. Any questions on entering it into the calculator? Okay, then I scroll and I hit calculate. And it gives us what's called F. So that's the F statistic. Okay, the test statistic is F. And I figured I'd show you what it looks like. So this is the book, and I programmed a piece of that. So here's the F distribution. Turns out there's two kinds of degrees of freedom. I'm not going to get involved, but if you have different amounts of degrees of freedom, you get slightly different curves for the F distribution. You'll notice that the F distribution is unimodal and skewed right. Any questions on that? Any questions? In fact, pretty much any degrees of freedom that you choose that are natural will be unimodal and skewed right. I'm not going to get into the details of the math for this because it's too hard, but I figured I'd show you a picture of what the distribution is. So in particular for our example, F was about 0.33. And if you go to 0.33, you're way over here. And the p-value is just like when you had chi-squared, you only have right tail tests. So the p-value is the area to the right of 0.33, which is really big. And in particular, the p-value was about 0.8. Any questions on that? So the test statistic was F is equal to 0.33, and the p-value was equal to 0.8. Any questions? All right, so now what we want to do is we want to look at that p-value, and hopefully you all know what to do. P-value is 0.8. So what do you think we can do? Very important at this point in the class, you know how to do this. The p-value is 0.8. What does that tell you? Yeah, drop the study, increase the sample size, exactly. And the conclusion is there is statistically insignificant evidence to conclude that, and now I could just copy and paste H1 because that's what we're finding that we can't conclude. At least 2 races have different population mean distances from the nearest library. Okay, so does that mean that they're all the same? Yeah, definitely not. Notice that we had a sample size for blacks and other of 4, and even white and Hispanic was a sample size of 6. a tiny sample size. So what that very possibly could mean is that our sample size was just too small, so we weren't able to get evidence. Okay, it might be that they're the same, but it might be they're different. We don't know. So when you fail to reject the null hypothesis and say there's statistically insignificant evidence, what you're saying is you just don't know anything. Okay, when you have a p-value of 0.8, it's not very helpful. Okay, it doesn't say they're all equal, but it's definitely not helpful when you have such a big p-value. Any questions on this example? Okay, so the hope is this looks like the other hypothesis tests we've done before. I mean, H naught is, 4 different equalities. In this case, H1 is a bunch of words. So we haven't seen symbols for H naught, words for H1, but now we're there. Whereas chapter 9 and 10 were symbols only for both. Chapter 11 was words only for both. Chapter 12 was symbols only for both. And now we're symbols and words. So, just get used to it. Any questions at all on this example of a hypothesis test? Okay, if they're not, I thought I'd do another example, but I'd have you involved in it. Okay, and that is, do you all listen to songs of the same length? Okay, so now we're just looking at you all. So first thing is, what is H naught? What's H naught? What's H naught?
mu sub 1 equals mu sub 2 equals ... mu sub n.
Okay, I'm going to go mu sub R equals mu sub S equals mu sub M equals mu sub J equals mu sub B. Any guess on what R, S, M, J, and B mean?
Why are there so many?
Ah,
Why are there so many?
look at the list of people that are here.
Our names.
Yeah, I use
Do you have one of those for each? No, wait, I don't get why that works. What is that? I don't.
Okay, so you have a bunch of songs you listen to, right?
Sure.
Okay, Sophia has a bunch of songs she listens to, right? Right, Marquette has a bunch of songs she listens to.
No, I'm asking. No, that's not what I'm asking. Okay, what I'm asking for is like, why are there so many? Like,
because there's a mean for each person who's here.
So in doing this test, you have to have one for each mean.
Right, because we want to find out, do you all listen to the songs of the same length?
Right.
So each of you has a population mean length of song that you listen to. Does that make sense?
Not really.
If you all listen to the same length songs, then the first person's population mean is the same as the second person's population mean, same as the third person's population mean, same as the fourth person's population mean, Same as the fifth person's population mean. So I just listed all the people because that's what the question is. It's you all. Okay. So I tried to, do the Southern way of saying it because otherwise it's more confusing. Because there's a bunch of you, and do you all have the same length songs? H1. And that is at least, oops, 2 population means. Actually, let's go 2 students, 2 of you have different population mean song lengths that you listen to. Any questions on that? Okay, now I'm going to put you to work and don't spend too much time.
Why at least 2? Why? I don't.
Why at least 2? That's H1. Same as the last one, at least 2 for H1.
Is it always at least 2?
Yep, because that's the opposite of saying that everyone's the same, is at least 2 are different. Do you see in my template here, at least 2 of the population means differ from each other. So for ours, it was 2 population mean song lengths. Yeah, so the opposite, okay, or the other side of the coin, if one side is all the means are the same, the other side of the coin are at least 2 are different. All right, so I have a task for you to do pretty quickly. I don't want you to spend more than a minute or 2. I want you to go online and go look up the songs. Just give me a bunch of song lengths that you have, maybe 5 or so, or some number of song lengths.
Wait, you want names of songs?
Not the names, the lengths.
Oh.
So in
Should they
seconds,
be in
probably is best.
seconds?
Probably in seconds. So go online, find the song, how long it is. Okay, it shouldn't take more than a few seconds to search Google or whatever. Or you could just ask your phone. That'll do it too. How long is, I don't know. How long is whatever your favorite song might be, whatever your favorite songs are. So I would go seconds. Yeah, I would go total seconds. Minutes, seconds is too hard mathematically to do. So just do it in seconds. Okay, and if it gives a minute seconds, multiply minutes by 60 and add it to the seconds. That's how you make it seconds. And just give me, not a whole lot. We don't have a lot of time left, so don't spend 5 minutes on it. Just spend a minute or 2. Shouldn't take long to find how long your songs are. Okay, so we got 18. Okay, so give me a list of your song lengths. Otherwise, it'll be too hard for me to kind of figure out. 1815? That's a 30-minute.
Hold on, I made a
Oh.
mistake. 1 second.
Okay, because that'd be a 30-minute song, and there might be some, but that'd be really long. Yeah, 6, 5, 8. So again, give me a list of at least some songs, more than one. A sample size of 1 can never work. So give me a sample size of at least 3, but maybe more if you have time in the next couple minutes. Yeah, 6. And hopefully you all can do it. Yeah, so if you get a list separated by commas is always best. See if it allows me to copy and paste. Yeah, it did. Good. I could copy paste into the Word doc. That's where it belongs. I think there's one more of you that needs to put it in.
I think that's everyone.
That's everyone?
Oh, never mind.
No,
Nope,
thanks.
one more.
Yeah, because I have 4. And sometimes not everyone's in. So I'm going to just use the 4 because that's all we've got. Give you a couple seconds. So we have SMJRB. So SMJ. Or do we have it?
Yeah, that's everyone.
Okay.
Actually,
Who am I missing? BRJ.
you're missing Marquette.
Okay, maybe I didn't get those in. Here we go. There it is. Chat boxes are always hard to get data from. Okay, so now I'm going to go to my calculator. Okay, and by the way, I had no idea whether whether the p-value is big or small. I have no idea whether you all have the same style of songs that you listen to in length. So now I'm going to just copy and paste. The good thing about the commas is I can do that. And then the second one. And the third one. And then the fourth one. Okay. And by the way, the assumptions that you have to make here, definitely normality. We have small sample sizes. Definitely standard deviation is the same because we know nothing about standard deviations of your song lengths. I have no clue. The bias or unbiased, I have no idea how you collected your data, whether you picked, which songs you picked, in terms of, because you might have 100 songs you like and you grab 5 of them or 4 of them. So definitely bias is an assumption. There's no bias. Independent, I think there's no issue. Okay, you didn't talk to each other about songs and stuff like that. So this is definitely independent, that we don't need to assume they're independent because this is definitely independent data. Okay, and I did ask you all in the same way to get those songs. So those 2 are not assumptions, but the first 3 are. Then we go ahead. Let's see what happens. Oh, look at that. Looks like we don't have the same song length, especially if using 0.05. So the test statistic is 4.27 about, and the p-value is 0.03. So let me just write p-value. Was equal to 0.03. So there is statistically significant evidence to conclude that, And the nice thing is, since I already typed it in, I can just copy and paste and make it not capital. At least 2 of you have different population mean song lengths of the songs that you listen to. Did I miss a data set? Okay, I was rushed because we're kind of out of time. But let's see. You got that data set for, oh, I guess so. So who'd I miss? 658, 130, 246, 189. 658, 130, 246, 189. Ah, because it was on the next page. Always does that to you. Yep. Now let's see if it changes anything. So let's do it. Ah, didn't change much of anything. In fact, now we even have stronger evidence, 0.02 instead of 0.03. So we're good. P-value is 0.02 now. Good rule of thumb, never do anything in a rush if it means anything, because I rushed through this. Okay, in terms of getting the data in. Any questions about ANOVA? Okay, I'm looking at the clock, and this is again our last chapter. We're done with the last chapter. Make sure you come on Thursday with things that you're interested in reviewing, because again, there's a lot of stuff. So what kind of examples would you like to see, and I'll make it happen. I'll also talk about the exam and the final, but we'll have your quiz, and then everything's gonna be different. It's not gonna be a regular lecture because there's no new material to talk about. I'm going to stop the recording now.